All right, let's continue with the collisions in multiple dimensions. So we were talking about we need to write the expressions in both the x and y directions. Okay, so what we'll do is we'll break our initial momentum into x and y components like so. So we have our P1 initial, and we can break it down into our y component and then our x component, and same thing with P2. Okay, break it down into our x and our y component. Okay, this should have a y here. Okay, then we can add these components together, right? Y with y and then x with x. And then from there, we will get our final momentum. We'll get those two components, okay? And remember when we were talking about vectors, that if I want that P final here, okay, and it'll have to be its magnitude first, we'll have P, let's say P2. Oh, that's just what they're calling it. Sure. We'll have our P2 final x. Well, I'll just say P final x, comma x. I don't know why they gotta make it complicated sometimes. Squared, P final y squared, and then square root that. Right? Remember when we were looking at, whoa, did not mean to do that. When we were looking at vectors, that this is what we would do, right? So we're essentially doing the same exact thing here, okay? And then if we want to find the angle, so the direction, so that would be like this angle here, we would want to take tan inverse of P final comma y over P final comma x. Okay, so again, it's the exact same thing. Okay, so we're going to go ahead and now apply this to a problem. So it's example 9.14. So it says a small car of mass 1,200 kilograms is traveling east, so we're calling that the positive x direction, at 60 kilometers per hour, and it collides at an intersection excuse me, with a truck of mass 3,000 kilograms that is traveling due north at 40 kilometers per hour. The two vehicles are locked together when they hit. Okay, what is the velocity of the combined wreckage? So again, if these were traveling in the exact same direction, it'd be much simpler. And we could say, okay, initial velocity equals final velocity, and boom, bam, there we go. We get that, initial momentum equals final momentum, not velocity, momentum, okay? But now we need to break this into components, and thankfully these are traveling just in the x and y axes, so it makes it a little easier on us, okay? But I'm going to go ahead and show you how you would do this. So we would have P initial, I'm going to say comma x, and P initial comma y. Okay, so in our x direction, we'll go ahead and look, and we just have this car, right? So we have mc times the velocity of the car, v sub c, and it's in the I hat direction. Okay, or whoops, I don't need to put that. Oh geez, eraser. I wish there was an easier way to do this, but I do not know of one, unfortunately. Okay, and then we have P sub I y, so that's going to be m truck times v truck, and that is in the j hat direction. Okay. Okay, so this is initial. Now we need to look at the final. Okay, and that's where it might get a little bit tricky because we don't know the final velocity in the x and the y direction. So let me think about this for a second. So, okay, yeah, so we should have some p sub x, final, and then p sub y final. I should have put those in opposite orders, but whatever. It'll work. Okay. And so, actually, it's fine. So in the x direction, we should have some mass, and since it says that they lock together, our total mass should be mc plus mt times some final velocity in the x direction. And then for the y, same thing, mc plus mt times some final velocity in the y direction. Okay, so this should be like I hat and j hat. Okay, and you don't necessarily need to have these up here, the bars or the directions, as long as you keep track of the x and the y here. Okay, you just have to be very careful with that. Okay, so now what we'll do is we'll take each of those equations, set them equal to each other, and solve for Vx and Vy finals. Okay, so let's do this one first. So I'm gonna go ahead and label this as 1 and then 2. So 1, we have mc Vc is equal to mc plus mt times v sub x. Okay, so v sub x then is going to be mc Vc over mc plus mt. Okay, so we can go ahead and plug all of this in. Our mass of the car is 1,200 kilograms. Our velocity of the car is 60 kilometers per hour, and typically I would change that into meters per second, but for the sake of this, I think it's okay to leave it in kilometers per hour since we're looking at this velocity in terms of vehicles, and typically we look at things in miles per hour, but kilometers makes it a little easier for us. Okay, so we're gonna say now divided by 1,200 kilograms plus 3,000 kilograms. So our final velocity in the x direction will be, let's see, plugging it into my calculator, I get 17.1 kilometer per hour. And again, this is in the x direction only. Okay, so we've got one piece of the puzzle. Now we need to do part 2 here. So we have to say, or look at the y direction. Okay, so we're going to go ahead and say for 2, we have mt Vt is equal to mc plus mt times our final velocity in the y direction, right? Yeah, okay. So then that'll give us v sub y is equal to mc plus mt. No, I'm sorry. Woo, getting too far ahead of myself. Did that wrong. I was doing it too fast in my head. Okay. We get mt Vt over mc plus mt. Okay, so v sub y then will be 3,000 kilograms Whoa. My mind is going too fast for my pen. Okay. 3,000 kilograms times the velocity of the truck, which we were given 40 kilometers per hour. Okay. And divide that by our mass of the car, which was 1,200 kilograms, plus 3,000 kilograms, the mass of the truck. And so we can put that into our calculator. 3,000 times 40 divided by 1,200 plus 3,000, we get 28.6 kilometers per hour. Okay, now we have both of these pieces. Now we can solve for our final velocity. Okay, that is going to be v sub x squared plus v sub y squared, square rooted. Okay, so the v sub x we found was 17.1 kilometers per hour squared, plus v sub y we found was 28.6 kilometers per hour. Square that and then get the square root of that. So let me put that into my calculator quickly. 17.1 squared plus 28.6 squared, square rooted. And I get our final velocity is 33.3 kilometers per hour. Okay, now this is just our magnitude, right? This is just our magnitude of the velocity. What if we want to know the direction? Because that's nice to know, right? So I'm going to go ahead and do that on the next page. Our direction then is going to be tangent inverse of Vy over Vx. So that'll be V sub y, which was 28.6 kilometers per hour, divided by 17.1 kilometers per hour. So I'm going to put that in my calculator. And I get a value of 59.1 degrees. So this is the direction of my velocity. Okay, so 59 degrees with a magnitude of 33.3 kilometers per hour. And that would be my velocity. Okay, so looking at this here, it would be about, I'd say about like that-ish. Okay, so this would be my about 59 degrees and my final velocity here. Okay? All right. So I will do the next example in the next video. Sorry, there was somebody walking by the window. I got distracted. But I will start off the next video with this example, and then we'll go from there. All right? I will see you in the next video.